good morning everybody and welcome to the November 3rd Thursday Web Forum. My name's Hillary Morris and I work on Blueprint User Support and Communications for the South Atlantic LCC. Your cooperative hosts this Web Forum on the third Thursday of every month right here at 10 a.m. to give folks like you a chance to ask questions and provide input to help guide the conservation future of the South Atlantic. So this agenda will be familiar to anyone who's a regular Web Forum attendee, but in case we have any newcomers, I wanted to quickly run through what to expect this morning. I'll start out by introducing our presenter, who will speak for 30 to 40 minutes or so. After that, there'll be plenty of time for questions and discussion. After that wraps up, we'll spend the last few minutes of the webinar on some updates from LCC staff, followed by an open discussion and time for anyone to ask questions. So before I hand things off to Simeon today, I want to go over a couple of logistics. Throughout the presentation, you're welcome to type any questions you have directly into the chat box. I'll be monitoring that, or you can hold them until after the presentation. Just remember that you can change who receives your chat using that little drop-down menu, so if you want everyone to be able to read your question, do send the note to everyone. And to speak up at any time, I'm going to put us in silent mode just to minimize background noise, so all you'll need to do is press *6 to unmute your line. And I'll put us back in unmute mode for the Q&A to make it easier for us to interact. So before I put us in silent mode, anyone want to speak up with questions, comments, or concerns? All right.
The conference is now in silent mode.
So presenting today, we have Simeon Yurek, who's an ecologist with the U.S. Geological Survey and a member of our very own South Atlantic LCC staff team. So he's going to be updating us today on some work he's been doing to model trade-offs between the ecosystem services and economic benefits of oyster reefs. So Simeon, if you'll just unmute your line, *6, and share your slides, you can take it away. I am passing you the presenter ball.
Hello, can you hear me?
Sure can.
Great. Let's see. Okay, can you see the slides?
Sure can.
Okay, great. Thanks, Hillary, for that introduction. As Hillary said, I'm working in a cross-agency position between USGS and the South Atlantic LCC. The LCC is a cooperative spanning most of the southeastern U.S., and it draws together stakeholders from different levels of government and non-government and also private interests such as land trusts. And I'll be presenting some work that I've been developing over the past year that is intended to support management of the coastal zone and fisheries at state and local levels. This is taking an ecosystem services approach, particularly looking ahead to future conditions and applying decision science and ecological modeling to predict future provision of ecosystem services under various scenarios of environmental change and decision making. So this is an extension of the current LCC blueprint work, which identifies areas on the landscape of high shared conservation value. And in considering future change, it's a good extension for integrating and working with our partner, the Southeast Climate Science Center, with whom we're also collaborating. So, like I said, we're about a little over a year into a 2-year project. It's not entirely complete. It's still in a preliminary results phase. There are 2 main areas of research. One is ecological modeling of oyster reef building, which is more or less completed, and 2, decision modeling of spatial restoration and conservation planning. For the second phase, I've developed the framework for analysis, and over the next year, I'll be working with stakeholders to identify important focal areas to apply this modeling. Throughout the talk, I'm going to use South Carolina as an example because the coastline is well suited to visualizing how ecosystem services can vary across the landscape. But I do also want to say we intend to apply this over the entire southeastern U.S. coastline. And in that regard, propose it as a method for scaling between larger regional and smaller local level planning. So the broad conservation questions that we're interested in are, what will our landscape look like in the future, and what will the value of its resources be? How does uncertainty about ecosystem dynamics and future conditions affect how and what we conserve today? Does our understanding of the current value of the landscape differ from the potential future value when many different future outcomes are possible? And finally, as I mentioned, how can policy and land use planning scale between large regional or national scales, such as the conservation blueprint, to smaller local scales, where stakeholder values, decision strategies, scientific understanding of the ecology, and associated risks, where those are identified explicitly? So the research approach that I'm taking is to develop simulation modeling that predicts ecological responses to management decisions and actions under varying scenarios of uncertainty in environment and policy, that quantifies expected value and associated risk of resources that are of interest to stakeholders, and that promotes learning from predictions as new information becomes available. So a little background on coastal management. Coastal protection has become an increasing concern given recent changes in patterns of sea level rise, tropical storms, hurricanes, and the uncertainty of the future of those. A large percentage of the population is concentrated in coastal areas, although it's not clear what level of resources are needed to protect them. Recent emphasis is being placed on quantifying the regulating protective services of coastal ecosystems, for example, these two papers here, because wetlands and benthic habitats are self-engineering and they're potentially lower cost options compared to hardened structures such as bulkheads, breakwaters, seawalls, etc. However, these are also complex dynamic systems, and the path from restoration to ecosystem service provision is not necessarily linear. So we decided to focus on oyster reef habitat for this project because the services described for it, such as on this slide, are very diverse, and there's also potential for trade-offs in their provision, which inevitably must be addressed. This table is from an economic valuation by Grabowski et al. For Oyster Reef, and it shows the services in the left column, and importantly, it distinguishes between the biophysical processes hypothesized to provision these services in the center column, and in the right column, the valuation methods. Both the processes and the valuation methods can vary over the landscape, but potentially in different and non-correlated ways. At the same time, these services likely interact with each other, although the valuation tends to look at them independently and not model them as interacting processes. So on the other hand, we know that, as I said, the habitats are dynamic and interacting and provide mutual protective benefits for each other. For example, salt marsh provides vertical structure through geomorphology that promotes oyster reef growth, and reefs mitigate some of the wave energy that erodes the salt marsh banks. So resilience of either of these habitats is likely interdependent, and it may be useful to consider the habitat mosaic as a target for restoration. And for that reason, creation of living shorelines has become popular over the last decade. These include various artificial structures that synthesize oyster reef and are placed slightly offshore in the intertidal zone. The goal is to provide a low-energy site leeward of them, and then the marsh grasses colonize them and expand outward from the shore, increasing the overall marsh extent and also stabilizing sediment. However, the structures such as riprap, for example, in the panel in the bottom right, can be expensive to construct, and one estimate is about $400 to $650 per meter. So it's unclear how cost-effective these methods are and how much vertical relief is required to stabilize the wave energy, but they are a good start and have had some success. oyster reefs are also vital to coastal economics as a fishery, and many historic reef grounds have experienced great fishing pressure. For that reason, restoration of oyster shelter reefs is a priority for fisheries management agencies, and I'll also add if these programs can be funded. Here are some images of the equipment used to implement these projects, and again, these can be potentially very costly. And I'll just point out in the bottom left is online description from the state of South Carolina from their Department of Natural Resources, just listing some of the reasons why it's important to restore shell. And perhaps most importantly, there's an inherent trade-off between the regulating ecosystem service of coastal protection and the provisioning services for fishery harvest. For example, harvest can disrupt the coastal ecology and thereby reducing the protection service, and alternatively, setting no-take reserves reduces the harvest available to fisher people. So in practice, these trade-offs fall along a conservation commercial management axis, and these tend to be sort of separated, where conservation is handled by some NGOs or state agencies or federal agencies, and fisheries are handled through commercial regulation. The restoration of oyster reefs, depending on either of these stakeholder perspectives, can be funded by separate authorities. And in some cases, it's too expensive for one agency alone to fund. So we ask the question of whether it's possible to achieve some middle ground along this axis, where both harvest and coastal protection are provisioned and interests of both stakeholders are considered, assuming some compromise from either side. An example of this type of mediation are the public seed source reefs in Louisiana, where general public can come in and collect seed, which are small oysters, less than 25 millimeters, and they can outplant them to their private leases. And there has been some success with this program. At the same time, it's important to consider the different sources of uncertainty which are likely to impact the future conditions of the resources. And we can partition these into different categories and quantify the likelihood of each occurring and the likelihood of the uncertainty impacting management decisions and vice versa, and based on expertise in each of these different areas. So these four groups are basically environmental uncertainty, which is also process, structural uncertainty, which represents our scientific understanding or theoretical or mechanical understanding of the ecology, observability, which is monitoring of the current state, for example, the indicators that the LCC uses, and finally our ability to manage for intended outcomes. So here's a way to visualize the potential effects of sea level rise uncertainty on coastal wetlands. I'm going to show a clip of a NOAA model which predicts migration of wetlands inshore as saltwater moves inland. These results represent a combination of different scenarios of sea level rise interacting with wetland vertical accretion rates. In this model, there are many possible combinations of these factors, but for now, just consider these to be a no accretion scenario. I've chosen a part of the South Carolina coast here, which you can see about 5 major drainages, the Charleston, Cooper River in the center. To the north is the Santee and the PD Waccamaw drainage, and to the south, the Ace Basin and the Salkehatchie River, Harbor River down by Beaufort, South Carolina. So I simplified the land cover categories for this to just show black as saline wetlands and red as developed urban area. Urban development is static in this model, and the medium light gray represents freshwater wetlands. So we can see the black areas migrating inshore. And I also want you to pay attention as the slides advance to the light blue areas, which represent potential unconsolidated shoreline, which may or may not be stabilized. So the main takeaway from this, for me, just at a glance, is how are we going to manage all of this unconsolidated shoreline? Again, the scenarios represent combinations of sea level rise and wetland accretion, and there are various ways of arriving at each scenario, and we don't necessarily know what will happen to the wetlands. And so several outcomes are possible. Will it just become submerged peat? Would it be good intertidal habitat? Will the sediment become disaggregated, redeposited on the marsh, or even flushed out of the system? All of this is uncertain. But from a management perspective, we can ask, are there practices that could prevent some catastrophic loss from happening? And if so, what types of structures would be best to engineer that are cost-effective and naturally sustaining? For this type of planning, it's also critical to consider how we value the landscape so that we can get a sense of what we're aiming to protect. So here's a snapshot of the South Atlantic's recently released Conservation Blueprint 2.2 for the same area in South Carolina. If you're unfamiliar with the blueprint and the LCC work, this is a coordinated effort to identify important areas on the landscape of ecological, conservation, and social value. The dark purple areas generally represent higher priorities for conservation action that have been identified by various stakeholder groups. And here on this map, you can see that the Santee River watershed to the north and the Ace Basin to the south both have a lot of purple. So these are areas that we are going to want to try to protect and conserve. But also flipping back to the NOAA slides, you see they also have a lot of unconsolidated shoreline, or at least potential for that. So to begin to address these potential changes in land cover, which most certainly will have an impact on the economic, social, and ecological value, we've taken a decision science approach of simulating expected ecological outcomes and their associated values and risk. So this figure shows a decision tree schematic of this process. We begin with our current understanding of values on the left column, such as, for example, set out by the blueprint, and include explicit management decisions in the second column, predicting ecological states in the third column under various scenarios of uncertainty and model parameters, represented here by the Greek letters, and then identify resources that stakeholders value, for example, harvest and protection, and finally calculate expected value in the future for that particular scenario and stakeholder. At the end, the net expected value and risk are tabulated across all of these scenarios. And I'll talk a little bit more about that later. So the oyster reefs can take various states depending on their age, successional phase, and level of fishing pressure that they're exposed to. Oyster reefs accrete on the left as individuals become stacked on each other through recruitment. Maintaining the structure is important for them for feeding and also for their survivorship. And dredging or tonguing the reef, which are fishing practices, break up that vertical structure and they can reduce the overall height of the reef. And this is indicated in the center by the gray dredged figure. So an important ecological question is, are there critical thresholds of reef height below which depensation occurs? And this is when the reef vertical accretion is unable to keep up with the processes that break it down. A few recent studies have measured this effect in restored reefs. And here's an example by Colden et al. For reef sites in the Great Wicomico River in Virginia, which is a Chesapeake Bay tributary. The figure generally shows that that oyster density on the left axis and oyster survival on the right vertical axis, both of those are related nonlinearly to reef height in this sigmoidal S-shaped relationship. And this suggests that there may be some thresholds possible where a certain restored reef height is necessary to sustain the reef. At the same time, the reef impacts itself and the hydrodynamics around it by attenuating wave energy that passes across the reef, and this can be modeled as an engineering problem. So here's a lab study by Allen and Webb done in a small wave tank, and they applied different treatments of reef heights and widths and measured the waves moving across, calculated a coefficient KT, which basically represents the overall wave amplitude reduction. And they compared it to a previous study identifying parameters of the reef and using equations to calculate KT theoretically, and they compared it to what they measured in the tank, and they found that they had pretty good agreement with those data. And so we can use these equations when we don't have good accurate measurements of wave properties at restored sites. And I also mentioned very briefly that the USGS has been deploying sensors through their SWAT program for salt marsh, measuring storm surge across the wetlands following major hurricanes. So here's a schematic of an oyster reef population dynamics model that's based on shell availability for recruitment. This model has been in development for about 25 years, beginning with Eric Powell and other colleagues, Hoffman, Klink, Sonyat, and others. And I've been working with a few folks at USGS. Hongqing Wang's one of them, and also Romain Laveau at Canadian Fisheries to develop it as an individual-based reef building model. I won't describe in too much detail, but I do want to point out that there are different life stages included, and the recruitment from larvae to spat and also the spat survival are both dependent on the availability of different types of shells: a crushed dead shell, which is the bulk of the reef, shell of live oysters, which occupy the top of the reef, and the box shell, which are intact shells from recently dead oysters. So there are a few sources of feedback here, and they combine to impact the accretion or depensation rates of the reef. There are also exogenous environmental factors that affect the population dynamics, such as salinity, fluctuation, predators, food availability, and disease. I've included a theoretical energy budget based on a field study from the UK of European flat oyster. And this budget describes how energy is partitioned into three categories of tissue, shell, and gonad. And this partitioning varies with age. So importantly, a higher abundance of older individuals on the reef would have considerably higher gamete production. And these rates could feed back into the size structure of the reef, the age and size structure of the reef. So there are equations in the model describing feeding, respiration, age-based mortality, and larval survivorship. These are actually pretty complicated, so I'll spare you sort of the gory details of these, but I just wanted to put them up briefly. So for the simulations, I pulled some water data from Scrine Creek, which is on Cape Romaine National Wildlife Refuge, just offshore of Francis Marion National Forest, near the mouth of the Santee River. And I took 1 year of data and just looped it over 100 years, and I took a pattern of chlorophyll from another study and made up some turbidity data. The bottom panel is more or less a toy time series. But I did this to just make sure the model was running the way that I had envisioned it and not behaving strangely. Just briefly, gamete production is a function of a gonadosomatic index, which is the proportion of gametes or gonad in the population, and it fluctuates, and I've added stochasticity to it. So once it hits 0.2 of the overall biomass, gametes are released. The reef morphology is a new addition, and this is just a simple trapezoidal geometric shape. I'm modeling the total biomass of shell, and then I calculate the height and area from those biomass values. Larvae recruit to the reef according to functions of available shell, and so this is the overall area of the reef, but also its rugosity, so to speak, insofar as there are live oysters there and how much spatial area each of the individual live oysters has. So recruitment is limited by shell area, and I'm going to focus on that aspect for presenting the results because this has been identified as one of the important focal areas for managing reef populations. So here are some results from the 100-year simulation, and there are 4 panels. Basically, the top 2 describe the reef dynamics, the bottom 2 describe the oyster dynamics, and I'll talk you through this a little bit. I just want to ask real quick, Hillary, is everyone still hearing me?
Yep, hear you fine.
Okay, great. So the top panel basically shows the reef growing in height and in shell biomass. And you can see it's accreting from about ground level to 150 centimeters over about 80 to 90 years. The second panel shows shell availability. Let's not focus on that one. The bottom 2 panels show the oyster biomass, total biomass for the 3 different groups, tissue, gonad, and gametes. And the 4th panel at the bottom shows the age and size structure through time. And I've broken it out into 4 groups based on size classes that have been used in the past. But I'll also say that this is an individual-based model, so I'm not modeling size classes per se, I'm modeling individuals. I just broke them out this way to visualize and compare to other studies. So one of the good things about the individual-based approach is you can look at various population dynamics rates, such as how many of the oysters are dying from natural mortality, how many are consumed by predators, how many become buried by other oysters through time, and how many of them die of old age, basically. And we've set a terminal age to between 6 and 20 years, and that's a stochastic function. On the right are pretty standard predator-prey functions. These are functional responses that also have stochasticity. So we can see for those that are consumed, how many generally are consumed for different prey densities. So another good thing about the individual-based approach is you can compare them to weight at age curves for empirical data. And again, these are the simulated oysters, but we can see that there is this seasonal pattern in the weight at age curve, and if we apply some length-weight relationship, you can visualize this for length at age. And I just compared the simulated data to an empirical study here in North Carolina in the Outer Banks in Pamlico Sound, Pamlico and Albemarle sounds, and I compared the simulated results to some predicted models, length at age models from those restored reef data. And the patterns look pretty good. The simulated oysters are growing a little bit more quickly, but they reach a similar height after about 2.5 years. I mean, similar length. Also, I won't describe this in too much detail. You can look at the the size structure varying through time compared to histograms from the empirical study. And the takeaway from this is that the histograms are fairly complex and a bit messy. And that's what I was hoping to achieve, and just to achieve some realistic performance of the model. So I'll just show a few more results real quick, summarizing what happens when you vary the recruitment parameter. And the recruitment parameter, shown with the red arrow, is just some parameter that I've set that is sort of a filter on how many larvae and spat can actually land on the reef. If you don't set this filter, it just grows indefinitely. So by changing the parameter, you get drastically different reef dynamics. So for example, in lowering it here to 0.005, the reef doesn't accrete above 70 centimeters, more or less. So it never reaches its maximum potential. So this could be a management problem if recruitment is low and the reefs are not growing fast enough to be sustainable. And so on this slide, there are two other versions of the parameter. On the top, it's higher, 0.008, and 0.007 at the bottom. And in the top, the reef grows very quickly over about 30 years, and this probably is not realistic. In the bottom, it's also growing very fast, but it also is having some strange dynamics. And I just want to point out in the very bottom panel that the age structure can be highly variable, and it's showing these 2- and 3-year oscillations, which have been described on natural reefs. That the recruitment can sort of vary at this scale, and the population dynamics can vary at this scale. So I will grab some water real quick. I'll sort of wrap this up by summarizing the next steps over the next year of how we want to apply this modeling, specifically for management and for creating living shorelines as are identified, as this need is identified by stakeholders. So here's just an example for South Carolina of taking a landscape view and considering each of different management areas as parcels or as assets in a portfolio of the entire landscape. So there are about 25 or so here, and I just summarized it as 8, but the gray and white boxes indicate selecting some areas for restoration or not selecting them. And again, going back to the decision analysis framework, the plan is to choose all possible management options, which is all possible combinations of restoring these different parcels and simulating the responses based on different key uncertainties, not every possible uncertainty, but key uncertainties such as drought or water availability or more frequent hurricanes or more persistent low amplitude wave energy such as caused by boat wakes and things like that. And the goal, again, is to arrive at an estimate of expected value from the perspective of a fisher who is interested in harvest and from the perspective of a coastal steward who's interested in shoreline protection. So we can take the results of these figures are just hypothetical, but we can take the results from each of these simulations and compare them, put each on its own axis, and sort of compare, get a sense of what are the biophysical limits of the system for provisioning both of these services. So on the left panel shows this biophysical space and just identifies theoretical preference zones. For example, the coastal steward in red and the fisher preference in blue, they may not necessarily overlap. But then we can ask on the right, are there such things as indifference curves, which are the dotted lines, which represent some sort of compromise that either is willing to take and consider that not much or no loss of value would occur moving along these indifference lines, and you can set different levels of compromise. So again, the gray dots in this panel represent the ecological system and what outcomes are possible and which are likely under different sources and different scenarios of uncertainty. The red and blue panels and lines represent a value, a stakeholder value, for viewing the resources in that system. So we'll be applying modern portfolio theory analysis to quantify expected value from each of these perspectives, and then you can compare this, as we've done before, and get a sense of what the trade-off space is. So here, on the left, the fisher value is weighted by how much the stakeholders identify the value of an oyster harvest portfolio compared to a wave attenuation or coastal protection portfolio. And these are summed together to get their value, and likewise with the coastal steward, and these weights are different for either stakeholder. Finally, in running the simulations, we come up with an estimate of the risk associated with all possible scenarios. And I'm not going to go through the equations for those, but these are taken from economics theory, from modern portfolio theory. But you get a sense that you can graph the utility against risk and ask stakeholders what level of risk they're willing to take on. And so this exercise becomes particularly informative when there are larger slopes in the portfolio risk efficiency frontier. For in this example, which again is just theoretical, between 0.2 and 0.4, the utility rises much more rapidly than the risk increases. So these are areas where you can talk with stakeholders and get a sense for what would be needed, what would we need to do to focus on these areas. So to summarize, the Oyster individual-based model combines metabolic modeling at the individual level with population dynamics, and this is a new development because either of these have been treated as different models, and so we're combining them here to get a sense of how those two interact to create the Reef. It again draws heavily from existing models, from both metabolic modeling and population dynamics modeling. Reef morphology is included, age and size structure is dynamic, and an energy budget is also included, and this links us up to folks like Romain Laveau, who have done dynamic energy budget modeling. He's done it in Louisiana, and so it would be good to compare his results to our results. And most importantly, probability-based parameters for recruitment to the shell are included, and these are parameters that we will want to monitor into the future because the reef accretion is appears to be very sensitive to them. So the next steps, I've sort of already described them, but apply the model across the landscape, pull bathymetry data, and whatever the best approximations of time series of environmental conditions, such as salinity, chlorophyll A, and turbidity. Simulate the uncertainty scenarios, estimate wave attenuation from the Vandermeer equations, and compare the values that we simulate for coastal protection, compare them to areas that have been identified as conservation priorities, where the conservation priority value is high. And this also changes across the landscape. Finally, we can compare the trade-offs between these two stakeholder groups, and we can talk about risks that they may be interested in or may be interested in avoiding. So again, just to sum this up, we've chosen these two groups as sort of toy models for potential trade-off among stakeholders. And we're proposing this methodology as a way of getting at the stakeholders by explicitly accounting for their values and also explicitly accounting for future uncertainty. So thank you everyone for joining. I just want to mention a few of my collaborators, and thanks to Rua for all the support he's given in this project, and also folks at the Climate Science Center, University of Florida. Megan Lapierre has been a great help. Romain Laveau has been a great help, and also we are developing the portfolio modeling with a group at the University of South Florida, a group of computer scientists. So thank you, and I'll take any questions.
Great, thank you, Simeon. I'm going to take us out of silent mode here.
The conference is now in talk mode.
So you should now be able to speak freely just by unmuting your phone. I'll pause here for questions. You're also welcome to type into the chat box if you prefer.
Hi, this is Ann Hugh-Ellis. I have a question. I was wondering, and you may have spoken to this earlier in the talk, but just the ability to apply these kinds of models to other landscapes, or to apply this decision framework to other landscapes, and what might prevent you from doing that, or what would be needed in order to do that.
Hi, Ann. Yeah, thanks for your question. The goal of this modeling was, when we were first talking about it, we set a rule. We need to be able to apply this even if there's lacking data, or if there are systems that are not very well studied. So that's why I've taken some sort of extra care to make a process-based model that draws from just a few landscape parameters. So we should be able to apply it in any system, sacrificing, of course, precision. But the main variables that are needed are bathymetry, food, which is chlorophyll A, and turbidity, and we can get these from remote sensing. And then we can go validate or ground truth with monitoring on the ground after we set predictions. Does that answer your question?
Yeah, it does. I'm thinking just about the efforts in Louisiana where they've attempted to model oysters in a variety of different ways, and the challenges that they've done so, in doing so. And maybe you've talked to Megan about that. And I suspect it's probably that chlorophyll is the limiting factor in doing this in Louisiana, just because there isn't good chlorophyll data. So I was just thinking about it, the applicability of this kind of work in Louisiana.
Yes, exactly. Chlorophyll is probably the most limiting, and we're coming up with new remote sensing ways of at least getting a monthly time series of that. And yeah, we've talked to Megan, and she will be working on the sort of ocean circulation model for the inshore basins. And Romain was her postdoc, and I've spoken with him, and we want to apply the energy modeling on top of what she's doing.
Sounds cool.
Yeah, thank you. Thanks for your question.
Great. I'll put the ball rolling for anybody else. We definitely have time for a few more. Quiet bunch. I'm going to pause one more time. Simeon, I guess that was just an incredibly thorough presentation. Thank you so much for that today. We'll pause again for questions and discussion at the end. So if something comes to you in the next 5 minutes or so, there'll definitely be a chance to voice that question. I'm going to take back the presenter power here and just wrap up with a few South Atlantic LCC staff updates. Bear with me while I get my screen shared again. So at this point, I usually give a preview of our upcoming web forum. I wanted to give everyone just a heads up that we are going to be skipping the next couple of web forums taken December and January off for the holidays and some LCC staff travel, but we will reconvene in February. I'm hoping that our February talk is going to be a little bit of a virtual panel discussion about some different partnership business models. But right now, officially, that's to be determined until we lock that in. So I'll be sharing more details of the February 15th web forum in the new year. Some updates from LCC staff. Simeon spoke to this a little bit, but Blueprint 2.2 was just released last week. This includes making all the version 2.2 spatial data available on the Conservation Planning Atlas, or the CPA. That's also updating the version of the blueprint that's available in the simple viewer, as well as the release of a blueprint implementation strategy and updating the blueprint development process documentation and all the metadata online. So please check that out and get in touch with me if you'd like to use the blueprint to bring in new resources for conservation or inform or prioritize your decision making. My role is blueprint user support, so that's my job, to assist you in any way that I can and help make sure that your feedback gets incorporated into future versions of the plan so it keeps getting better and better. And then here I'm going to hand things off to Mallory briefly to talk about the Southeast Conservation Adaptation Strategy Symposium that was held at the Southeast Association of Fish and Wildlife Agency Conference earlier this month. Mallory?
Hi folks, Mallory Martin here. I'm the coordinator for the South Atlantic LCC, and just to give you a real quick update on the Southeast Conservation Adaptation Strategy that was featured at a symposium in conjunction with the Southeastern Association of Fish and Wildlife Agencies meeting 2 weeks ago in Louisville, Kentucky. The symposium was titled Aligning Actions for Success, and one of the things that it featured was a group of presentations around aligning those actions and focused really on integrating state wildlife action plans into the objectives of the CCAS blueprint. And then those presenters were supported by a facilitated dialogue which revolved around a number of themes, one of which was reinforcing the value and the need for working at the scale of the entire Southeast, 15 different states, and reinforcing that need and that value. The symposium also featured the latest update of the CCAS, the CCAS blueprint itself in version 2.0, which included the incorporation of version 2.2 of the South Atlantic Conservation Blueprint, as well as integrating other sub-regional conservation planning efforts. So the CCAS blueprint itself is up and covering a geography of 15 southeastern states. Had a very successful symposium at the CIAFWA and moving forward with continuing advancement at that regional scale.
Thanks, Mallory. If you're interested in learning more about CCAS, I'd point you to ccasssoutheast.org, or the Southeast region has its own conservation planning atlas where you can access all of the spatial data for version 2.0 of the CCAS blueprint. So if the South Atlantic doesn't cover your entire region of interest, perhaps you work at the scale of an entire state, the CCAS blueprint can be a really great way to make sure that you're getting that large landscape view spanning LCC boundaries. So I always like to wrap up letting people know how they can get more involved with the South Atlantic LCC. I definitely encourage you to join our web community by creating an account on the website. That'll get you signed up for our monthly newsletter and a monthly reminder about this web forum. That'll be sure to alert you to opportunities to get more involved, to serve on teams, etc. You're always welcome to reach out to staff like me or Mallory, connect with other members of your cooperative, and then, of course, explore the conservation blueprint online and let us know how it's working for you. I'll pause again for questions here. We're still in that open talk mode, so if you want to speak up, just unmute your phone. All right, hearing none, let's call it a day. And in 7 minutes early today, so enjoy your 7 minutes until your 11 o'clock call. Thanks for joining us this morning. Thanks again, Simeon, for presenting, and hope to hear from everybody when we're back on the web forum in February.